Hello everyone, today I want to talk about a DVB-S receiver and I'll use a practical signal to explain the processing steps. Before anything, let me mention again that I will not focus on the demodulator here, because you can refer to the previous video about QPSK demodulation for that part. Today, I'll focus on decoding steps in detail and highlight the key steps involved in DVBS decoding. As you know, a DVBS transmitter looks something like this. The architecture is based on ETSI standard. This document number EN300 421 V1.1.2. As you can see, this is the complete block diagram of a DVB-S transmitter. And for building the receiver, you need to reverse all blocks starting from the end. And of course, the first step on the receiver side is the QPSK demodulator. DVB-S uses concatenate coding. That means Reed-Solomon, interleaving, convolutional coding. After QPSK demodulation, we start with the Viterbi decoder to decode the convolutional code. Then we apply the convolutional interleaver, and the output bit stream is passed to the Reed-Solomon decoder. Finally, the output is descrambled. All the details of the DVBS protocol are described in the official ETSI DVB documentation. But QPSK mapping and code rate. On this page you can see the QPSK mapping, which is query-coded. This section shows the details of convolutional code rates, including the puncturing patterns for different rates. Here we also have the structure of convolutional interleaver and the interleaver. But about the convolutional interleaver structure, as shown, the interleaver has depth number of branches, I equal 12, delay unit is equal 17, M equal 17. In the transmitter, branch 0 has no delay. Branch I for start from 0 to 11 has a delay of I multiply N. For example, branch number 1 has 17 delay. Branch number 2 multiply 17, and until the branch number 11 has 11 multiplies 17 delay. But what convolutional interleaver? In the receiver, the interleaver must apply delays in reverse order. That means branch 0 has 11 multiplies 17 delay, branch 1 10 multiplies 17, and until the branch 11 has no delay. This ensures that all signal paths following the transmitter-receiver combination exhibit identical delay. Bit-stream synchronization sync-word. A key point here is that after Viterbi decoder and before the interleaver, you need to synchronize the bit stream. According to the ETSI standard, the bit stream fed into the interleaver or the interleaver should start with either inverted sync byte hexadecimal B8 or the normal sync byte, which is hexadecimal 47. Reed-Solomon decoding and descrambling. After the interleaving, the bit stream goes through the Reed-Solomon decoder according to the ETSI standard. You can find the details of the RS decoder presented here in a ETSI standard. As you can see, this is a generator polynomial, and this is a field generator polynomial, and this is a shortened Red Solomon, and it's shortened by 51 bytes. Before the descrambler, we need to synchronize the bit stream as follows. The sync pattern begin with an inverted sync byte. I mean B8 in a hexadecimal, followed by 7 occurrence of the standard sync byte hexadecimal 47, each space at regular intervals. Then the descrambler is applied using a specific generator polynomial and structure as defined in the standard. The details presented in this page you can find simply scrambler generator and also the initial state of registers. But uh, for implementation in GNU Radio, now I show you how we implemented this complete process. Since QPSK has a 4-phase ambiguity multiple of 90 degree, we resolve it by multiplying the signal by constants. It can be 1 or -1 or 1j or -1j, and checking the bit stream after viterbi decoding using a frame length of 13,056. You should be able to see the sync pattern, I mean 47 hexadecimal and inverted sync, B8 hexadecimal in that frame length. We have got two main ways to implement viterbi decoding. One is by using FEC extended decoder here, and you will need to define a convolutional decoder settings and a punching pattern manually. The other option is a viterbi decoder block made for the DVB-T. It follows the ETSI standard and is much more user-friendly, which makes it a great choice for this scenario. Here I visualize the viterbi output in a MATLAB using this frame number, and as shown we can detect the correct sync pattern, which confirms the ambiguity is resolved. If you can uh, see the correct sync pattern, you have to change the phase rotation by one of that 4 option I mentioned. I mean, you should use a constant multiplying a constant in a signal that includes one of these 4 options, 1 or -1, 1j or -1j. Bit stream synchronization with GNU Radio to align the start of each frame with inverted sync, I mean B8 hexadecimal or 47 hex, we need a synchronization block. Unfortunately, GNU Radio doesn't have a built-in DVB sync block, so I implemented a custom Python block for this purpose. I didn't spend much time writing this block. I actually used AI to generate the code. While it functions correctly, it's not professionally optimized. There is definitely room for improvement and more efficient implementation, but for now it serves its purpose in demonstrating the decoding steps. Implementing this code using AI involves some subtle considerations such as ensuring it functions correctly in the presence of errors, carefully defining the block type and its inputs, possibly needing to refine certain parts of the code for proper execution. Convolutional deinterleaver in GNU Radio. In the deinterleaver block, set the number of ship register equal to the interleaver dips and set the delay number to m equals 17. In fact, in GNU Radio, the convolutional deinterleaver, the number of ship register is equal to the interleaver dips and um, the depth of ship register is in fact equal with a delay in a standard. Final steps. Finally, we connect the output to the read Solomon decoder configured according to the ETSI DVB-S specification, and after that the energy descrambler block at the end performs the scrambling exactly as defined in a standard. It's a famous descrambler generator. At this point, the output is a TS packets. The key point here is that this block first synchronizes the input bit stream using an inverted sync byte of hexadecimal B8 and a frame length of 13,056. Practical signal test. I have tested this DVBS receiver design with the practical signals, which is a satellite signal. I won't go into further detail about that signal due to YouTube policy restriction on sharing sensitive RF links or information. Here I'm presenting the MATLAB into visualization with a frame length of that value corresponding to the TS frame. It's equal 188 bytes. This is as you can see, this is TS contour, and here is this is a TS header, and it starts with 47 hexadecimal, and it's confirmed or design work perfectly. In the end, thanks for watching. I hope this video was helpful.